All right, so now we're going to talk about how to take a limit, and a little bit later we'll deal with continuity. But first of all, the definition of what a delta disk is. So you would have dealt with epsilon delta proofs, or at least definitions for how to take a limit and even how to take a derivative of a function. So we're taking a disk, and all right, they're saying an open disk of radius delta around the points A, B. So we've got an X component and a Y component. Remember, that's an ordered pair. So this is going to be centered at AB. So if you notice the equation for a circle there, we've got a less than that delta squared. So in this case, delta is the radius of the disk. And there's a little picture of it right here. So you've got point AB. In this case, we're looking at 2, 1. You can put a disk around it. However large that delta is the radius. The idea is to get closer and closer and closer and closer to that point by shrinking delta, shrinking the radius. This is the same sort of thing you did when taking a look at the limits. As you get closer and closer and closer to the value that just has an X component, you see where you are with relation to the Y component, the function component. So we've got a definition down here, more formal. So you have a limit at some value L if the limits as the ordered point xy approaches the given point AB. So as the x's and y's get closer and closer to AB, the limit of the function will equal L if it exists. Now, the epsilon delta proof, or the epsilon delta definition before, basically says if for every epsilon greater than 0, we can take, we've got the epsilon over here, the function, the distance between the function and L is smaller than that epsilon. That's for every epsilon, essentially approaching 0, essentially. Then there exists. That means we can show at least one delta greater than 0, such that for all points in xy in a delta disk around AB, except possibly for AB itself, that allows for a possible hole in the thing. So if you remember from Calculus 1, when you were solving for limits, you could have a limit even if there was no actual value at the spot. So as long as the function, essentially the distance from the function and that value L gets very, very small, whenever you have the distance between those 2 points smaller than delta, but strictly greater than 0. It has to be something, all right? And again, you're talking about infinitesimal things. We won't be discussing this. I'll be discussing it right now, but we won't be worried about the ball for 3 dimensions or higher. So in this 2-dimensional space for the xy coordinate, it'll be on a plane, so we're looking at a disk, but in 3 dimensions, you're going to look at an XYZ ball. So think of it as a sphere that gets closer and closer and closer and closer to the point. And this is the equation for the distance of that sphere from delta. If you have a 4th component, well then you add this, a 5th will add another one, a 6th, and so forth.